Hey everybody, let's go over this second order circuit. Okay, so we have two switches, and if you think about it, when this switch is in position A, and then this switch over here is in position D, this resistor, this end of the resistor is not plugged into anything, right? It's just floating. So you can basically just ignore this resistor for now. So we basically just have two circuits like this over here and over here. Okay, so what's going on with those two? So over on the left, we have that voltage source going, so it's kind of, you have current going like this, right? Through the capacitor. And if it was like this for a long time, then for the capacitor, the current is like this, C dV dt. And whatever is going on here with the voltage across this capacitor, it's constant. It's been like that for a long time, right? So, and the current is constant. It's been like that for a long time. Okay, so if the voltage is constant, then look, what is the time derivative of a constant? 0. So this is 0, which means the current through the capacitor is 0. So this is getting messy over here, right? So the current over here is 0, but it's all in series like this, right? So that means the current going through the resistor is 0, which means the voltage across the resistor is 0. All right, so if it's whatever the voltage is here, it's the same over here, right? Across is 0. And if it's 15 here, then it's 15 here. So in other words, the voltage across the capacitor before, when the switch is still in position A, is 15 volts. So like this. And then the voltage for a capacitor cannot change instantaneously. So if it's 15 volts before we hit the switch, it's going to be 15 volts after we hit the switch. So that's what we got from over here. Okay, and then this side over here, we have current going kind of, it can split, right? Some of it can go this way, some of it's going to go this way. But then again, it's been like this for a long time. So that means for the inductor over here, for an inductor, the voltage is L di dt. And the current going through there is constant because it's been a long time. So that means the time derivative of a constant is 0. So the voltage across the inductor is 0, which is the same thing as saying it's a short. It's like a wire. Now if you look at this, the current, some of it is going to go this way, some of it is going to go this way, but not really, right? If this side is a short, a wire, all of the current is going to go that way, and the resistor gets none of it. So all 60 milliamps goes this way, up. Okay, and then it kind of just depends how we label. If we just label this voltage this way, then we can call that the current going through the inductor before we hit the switch is 60 milliamps going up. And then if I label it this way, then I'll call that negative 60 milliamps. And then the current through an inductor cannot change instantaneously. So if it's negative 60 milliamps before we hit the switch, it's going to be negative 60 immediately after we hit the switch. Okay, so we got these two from this and this. Okay, now what? After we after we move the switches over, then it's just going to be this capacitor, this resistor, and this inductor. And then we know the initial conditions for the voltage across the capacitor and the current going through that inductor. And this is going to be a natural response. Okay, I was going to just write the answer, but maybe it's good practice. Where does this come from? So we can describe the voltage across over here. Right, so the voltage for an inductor looks like what? L di dt. Okay, hold on. Okay, and then I already wrote that down over here. Okay, these two. All right, so the voltage across here is the same as here, is the same as here, right? They're all in parallel. So then the current gets split up. So the current, just KCL, this current plus this current plus this current equals 0. The current for an inductor, we have the voltage. To get the current, we have to move dt on this side, v dt, and then divide by L, and then integrate both sides. Right, so then the current through the inductor looks more like 1 over L, and then integrate v dt plus whatever the initial condition was. Okay, and then the voltage across a resistor is just V over R. And then the voltage across a capacitor is right here. Oh, sorry, the current going through a capacitor is right here. Okay, so this is from KCL. But I don't like having this thing here, right? So let's just take a time derivative of the entire equation. So time derivative of this would just be V. Time derivative of a constant is 0. Time derivative over here, dv dt. Time derivative of this, second derivative. Okay, so now we have this second order ODE. Let's clean this up. Let's divide everything by C. There. Okay, and then let's just factor a 2 out of, I don't have to write that 0, right? So see this 1 over RC, I'm going to times 2 divided by 2. Because I just want to use the quadratic formula. Okay, so, and then I'll replace 1 over LC with omega naught squared. So omega naught is the undamped natural frequency. And I'll replace this with, that's the Nieper frequency. Okay, and then I don't want to repeat the entire lesson, but we can just generally say the voltage looks like some kind of something like this, which there's going to be 2 terms. And then if you substitute this solution into, oh, let me just write it generically. Some generic solution like this, and then plug this in here and here and here, then you're going to get this. Which is the characteristic equation, which is a quadratic. So what are the roots of this quadratic? Just use the quadratic formula. Like this. And then if we plug that back into that solution, which I erased, which I shouldn't have, then the answer is, we have 2 terms, e to the minus, At this point, it depends on if this is underdamped, overdamped, and critically damped, and I actually need numbers, so I have to actually use a calculator. Okay, so alpha, this Niebuhr frequency is 1 over 2RC. Okay, and then this undamped natural frequency would be 1 over LC. Actually, this is omega squared, so like this. Okay, I'm going to pause, punch these in the calculator. Okay, so I just punched the numbers in the calculator. I just used the values. R is 100 ohms. C is 10 to the minus 6 farads. And then L is over here, 0.0625 henries. Okay, so I just plugged those numbers in the calculator. So now I got these. So notice that alpha is larger than omega. So this is overdamped. Okay, and then you just look up for an overdamped system, the answer looks like, the solution looks like some arbitrary coefficient e to the minus s minus alpha minus this. Oh, I'm going to replace that with something so I don't have to keep writing this whole thing. Let's call this h. And actually, when I look at the numbers, it's 5,000 squared minus 4,000 squared square root, which would just be 3,000. Okay, so for this particular example, this is 3,000. Okay, so again, the solution is arbitrary coefficient e to the minus alpha plus h times t. Arbitrary coefficient e to the minus alpha minus h t. Okay, and then you can look up that lesson on overdamped, underdamped, critically damped. So this is the solution for an overdamped response. Okay, can I just plug in the numbers here just for e to the minus 5,000 plus 3,000 be minus 2,000. And then minus 5,000 minus 3,000 is minus 8,000. Okay. Okay, so we have this is an answer almost. We still need to figure out what is A1 and A2, our coefficients. So how do we do that? We need the initial conditions, meaning V at t equal to 0 would be A1 e to the 0, which is 1, plus A2 e to the 0, which is 1. Okay, and then what is the voltage when t equals to 0? We got it right here, 15. Right, the voltage across the capacitor. Oh, sorry, I just noticed in my drawing, I wrote the letter. This is the capacitor and this is the inductor. Okay. The voltage across the capacitor is 15, but they're all in parallel, right? So across here is 15, across here is 15. Okay, so the voltage at t equal to 0 is 15. Okay, so we have one equation. We need one more equation. So we can use dv dt. Okay, so let's take the time derivative of this. So that would be minus 2,000 A1 e to the minus 2,000 t plus negative 8,000 A2 e to the minus 8,000 t. And then we need dv, the initial condition, at t equal to 0. Right, which would be minus 2,000 A1 e to the 0 minus 8,000 A2 e to the 0 equals, what do we what is dv dt at time equal to 0? I don't know. We got this. Okay, so what do we do here? Okay, so we need, take a look at this, dv dt. Where do you see dv dt? Multiple choice. Right here, that's dv dt. So that means we need to look at the capacitor, right? Because that's where we're getting dv dt. Let's look at the capacitor. Okay, so we got the current for the inductor, because here, this is the current for the capacitor. But I don't know the current for the capacitor when t equal to 0. I know the current for the inductor. So how does that help us? Okay, so take a look at the voltage at t equal to 0 is 15. How does that help us? So the voltage from here to here is 15. From here to here is 15. That actually means I know the current through the resistor. Let me reclaim some of this space here. Okay, so the current through the inductor at t equal to 0. Got it. Negative 60 milliamps. What about the current going through the resistor at t equal to 0? It's V over R. And the voltage is 15. Right? So 15 over 100, 0.15. 150 milliamps. Okay, so I know the current through the inductor, I know the current through the resistor, and then just KCL, I mean, if it's 60 milliamps going this way, 150 milliamps going this way, then what's going on over here? It's gotta be 60, 100, no, 90 going this way, right? Because KCL, this plus this equals 0. So there you go. From KCL, the current through the capacitor at t equal to 0 is, well, let me say IL plus IR plus IC equals 0. So I'll just move these on this side of the equation. And then that is minus 90. Okay. How does that help us? This goes here, right? So let me write that. The current through the capacitor at t equal to 0 is C dV dt at t equal to 0. So then let's just move this over here. So dV dt at t equal to 0 is this. Okay. So back to where we were over here. This is I for the capacitor at t equal to 0 divided by the capacitance, which was negative 90 milliamps, and this is 1 microfarad, 10 to the minus 6. Okay, so there we go. Let's see. 90 milliamps is minus 0.09 divided by 10 to the 6 is times 10 to the 6. So that is 90,000. I'll just write 90,000. Okay. There you go. And then if we just divide this whole equation by 1,000, minus 2a1 minus 8a2 equals 90. Oh, sorry. That should be a negative. I lost my minus sign, right? Because this is negative 90. Okay, so we have two equations. And two unknowns. Actually, maybe I can just solve it right now, right? So let's see. A1 is 15 minus A2. Actually, let me just write these two next to each other. right? So we have two equations, two unknowns. Let's just 2 times 2, and this is 30. Right? Add these two together. What do you get? Negative. Oh, sorry. I lost my minus sign again. Okay. Add these two together. Negative 6a2 equals minus 60. So a2 is 10. And then a1 plus a2 is 15. So a1 equals 15 minus a2. So a1 is 5. So there you go. a1 is 5, a2 is 10. a1 is 5. I'm just going to write it here. a1 is 5 and a2 is 10. Okay, so this is the answer. Okay, so there you go. It's kind of a long explanation, but it's a video, right? So if you need to rewind some parts or pause in some places, and then let me know if you have any questions about this, and keep on studying. I'll see you on the next video.